So we have to start it. Yeah, okay. So actually today's class what we're going to say is tuning of PID controllers. Okay, online tuning of the PID tuning of controllers. Tuning controllers. We're going to see there are three tuning methods. Okay, online tuning methods. Online tuning methods. We have three methods: manual tuning method, Ziegler-Nichols tuning method, and Cohen tuning method. Okay, man. If we go into the first method, manual tuning method. The manual tuning method is nothing but we have to tune the system functions manually to get the stability of the system, and to get the stability of the system. So it takes some more time. It takes a lot of time, and also we need some more experience to tune the entire controllers. If it's a proportional PID, that means proportional intercontrollers, you have to tune manually by trial and error method, and you have to fit the system response to get the stability system. Okay. But if we come into the Ziegler-Nichols method, this method is the most popular method. It is used in more than 6 decades ago, and parallelly we can able to find these things contained in this next slide. Next slide. That means yes, this is the system response what you're getting from that function or from that system. Okay. Here what happens? There are some fluctuations are there. So top layer higher frequency and comes lower frequency, somewhat frequency. Again comes lower frequency. You're not getting the stability system. Again, this is for one KC. That means KC is nothing but KC is nothing but controllers. KC is nothing but here we can say that some critical value. Okay, case critical value. So what happens here? KC, what happens is here is somewhat high and somewhat low. So I'm coming to next slide. Next slot again is also like somewhat lower frequency is there. Again the critical value is coming high. So okay, what happens? Lower frequency to high frequency. This fluctuation is having there. So for this KC's value is 4. Okay. Again, if you come into next period, yes, we can able to get some fluctuations. Okay. We can able to get the system response. Okay, in a stability way, okay, without any higher fluctuation, lower fluctuation, and I can able to find the KC is 3.5. The critical value is 3.5. So what it indicates, if the critical value is 3, we are having some fluctuation, and if we are having this fluctuation, still we are having the fluctuations. Okay, for the critical value 4, and if we come into 3.5, yes, we can able to get the stability. It indicates even though if you apply the KC is equal to 3, you can able to get this fluctuation, and KC is equal to 4, you can able to get this fluctuation. So what happens? The stability response is, lies between this KC 3 to 4, that is KC 3.5. Once if you find the KC critical value 3.5, you have to apply the corresponding KP. That means corresponding whatever controllers you selected. If you select a proportional controller, you have to apply the KC value here, and you have to find the proportional. What's the KP value? Proportional gain. Again, if you selected proportional interval controller, you apply the KC value here, and you have to find out what's the proportional gain and interval gain. If you select the PID controller, we have to apply the KC value, that means critical value here, and find out what's the proportional value, what's the interval value, and what's the derivative value. Okay, so what's advantages is it's an easy method. Okay, to change the controllers, and also by changing once you find that critical value, it's very easy to find out the controllers by keeping the same critical values. Okay, and we have to here what happens PC. What in by PC means ultimate period. For example, for one oscillation, so if we can be able to find it here for one oscillation. This is a we can able to find from one oscillation what's the starting time, what's ending time, what's the time period taken for this one oscillation for the stability response. That is called as ultimate period, which is called as PC. In this graph, we can able to find that for critical value 3.5, you get the stability of system, and one oscillation, that is ultimate period, takes 10 seconds. Okay. If you apply these two values, you can able to find the remaining gain of internal controller, derivative controller. Okay. Once if you find all the gains, you can feed all the gains in the system. You can able to get the stability of the response as quick as possible. Okay. So what happens here? What's the disadvantages means it's again a time consuming process. Okay. But when comparing to manual tuning method, the time consumption is very less. And parallelly, once if you find the proportional gain value, it's very easy to find out the remaining interval values and derivative values. Okay. So what happens? The same thing you're going to find out in that MATLAB. So try to open the MATLAB, and I already framed the system like this. So like this, just a minute. I already worked the thing and done. So I want to open the system. Already what I worked with here. So experiment number 6. Yeah. So we are having step signal, and we are having on sum. Okay. And PID controllers, transfer functions, mux, and telescopics. Okay. First I'm going to select the mux. proportional controller. Okay, so try to click the proportional controller value. Okay, so for first order, second order transfer function, this is the system what I framed is for second order system. So try to click the proportional controller and go to proportional controller, so P. Okay, what happens? I try to find it here 100. Okay, and find out what's the response. Try to run the system. Try to run the system and find out. See, the fluctuation is going like this. At one instant it's coming down. So we have to minimize this fluctuation. Okay, that's called as the, so instead of the initial stage is going somewhat higher fluctuation, you have to minimize fluctuation, and the initial stage itself you have to cut off this error and find this and locate the system should be stable. Okay, by minimizing these errors. What happens again to try to change it 3000 by clicking, try to change the values manually and try to run the systems and again find out what scope is coming. Yes, straight is coming. Okay, straight is coming, response is like this. See, so the response is coming like this. Somewhat again you have to respond this fluctuation. Okay, what I'm saying that try to go for 1 lakh and try to run the system and find out what the scope is, what output is coming. Yeah, somewhat different fluctuation is there. See, somewhat is going on. Okay, so what happens? For example, if I try to fit to the 300, you have to find it manually. Okay, I'm going for 300. Okay, so what happens? Yes, I'm getting the response and try to run the controllers and try to run the systems and find out what the response is coming. Okay, it's somewhat coming like this. Okay, so what happens here? So where is the KC value means? Here what happens? You can able to, from this year you having some fluctuations there. Okay, so here what happens? You can able to find from year to year. From year we can get the stability system. At one stage we get the stability systems. See, so this fluctuation is constant for year. Okay, so what happens? You have to find the KP. For KP value 300, you're getting this thing, and you have to find what's the time period. So further you have to go for zoom x-axis. From starting from year to year, here you get the standard stability of the system. So I'm going to zoom this x-axis from selecting to this point to this point, as what I said in the PPT. So what's the difference is coming? What's it? This is called as the ultimate time period. Okay, 4.8 to 5.15. Okay, so for 4.8 to 5.15 means 5.15 minus 4.8. Yeah, 0.35 is coming. Okay, that's a time period is 0.35. And what happens here? You have to go for reverse process. That means you are not going to find the critical value. So we have to go. We're going for inverse. For the proportional error, for proportional gain, we given the 300. Okay, and we find the PC. Okay, so we know the formula here. Come here. You know the formula. For example, we take the PID controller. KP is equal to 0.6 kc. So here what happens? Already we know the value. KP is equal to KP is equal to 300 divided by 0.6. Okay, is equal to, what's the value is coming? So 300 divided by 0.6, 500. So KC is 500. Okay, once if you know the value KC, what happens? You can apply this value. Okay, so 2 into 300 divided by PC. PC is what here? PC is what? 0.6. So 600 divided by 0.6. 600 divided by 0.6. Sorry. 600 divided by 600 divided by 600 divided by 0.6 thousand. Okay, so what's all is coming here? 1000. Okay, so next we can go for KD. This gain, what you get is the interval gain. Then go for next gain, derivative gain. KD is equal to KP. KP is 300 value into PC is 0.6 divided by 8. So that happens 300 into 0.6 divided by 8. So 22 point. So KP is equal to, just a minute, KP is equal to KP PC divided by 8. 22.5. Okay, this is what the values we got it from the graph. Okay, from the scope, that means output. Okay, so already we have in the output. What's output you are getting here? This is a stability system. Already we have applying KP, that means proposal gain is 300. We got in the response, so you have to find. Still the response is coming here. Stability. You have to find out what's the response starting from the what's the time period taken for one oscillation. You have here find that 0.35. Okay, what I done the calculation previously, and go to the number 6. Yes, KP is for KP 300. You're getting the PC is 0.6. So once we know these two values, you can able to find all the remaining values and try to apply the same value by changing the proportional control to PID controller. So what happens? We can find the response and go for PID. Okay, 300 for 300. I'm selecting this 1000, and this is 22.5. Okay, so I'm changing the PID controller. Okay, with the proportional controller, I find out what's the gain for internal controller, what's gain for derivative controller, and I apply all the gains in the PID controller and try to run this stability and try to run this system. What happens? See, the entire array is minimized here. We can able to find this graph. We can able to enter in the previous graph and this graph. Okay, since having so many fluctuations here, from that fluctuation you can able to find the ultimate time period. Here what happens, by applying all the values, what happens, the fluctuation is reduced. Okay, this is one of the tuning method. What's the name is? Tuning method name is Zegers-Nicholas method. Okay, what's the difficult task here is we have to find the KP value, proportional gain value, by manually. Okay, manually. That means somewhat rough values. We have to find it. Proportional. You have to find out the proportional value manually, and you have to apply it in that. And the remaining formulas, and you have to find out what answer is coming for you. Okay, once you find the answer, you can able to run the response. So what happens, from the proportional controller you find the value of PC, ultimate time period, KC, that means critical value, critical interval gain, derivative gain, and applying all the values here, and applying all the values here. Okay, and applying all the values here, I find the response that is coming here like this. What happens, the initial error is minimized, and we'll get the defined output with respect to the real values, with respect to the what I input giving here in the system. Okay, so that is the advantage of Zegers-Nicholas method. That is advantage of Zegers-Nicholas method. Okay, when combined to manual method, this method is a somewhat good method. And I'm coming to next method, Cohen and Coon tuning method. Okay. So what happens, so we have to conduct this method. Then some of this method is also discovered after the Zegers-Nicholas method. Okay, so this method is depending upon 3 parameters. First one is tau d, that means dead time, and again is tau, that means we can say that's tau or tau au. Okay, tau means dead time, and tau means td is dead time, and tau is time constant. Okay, another one is GP, that means process gain. Process gain is calculated with respect to the change in the process variable by change in control output. Okay, in terms of percentage. So GP is equal to del PV by del CO, and parallelly there are 3 parameters of the GC: process gain and dead time, TD. Okay, and next one is tau is time constant. Okay, so and one more condition is that okay, so we have to take the once the process variable reaches 63%. Once the process variable reaches 63%, okay, so we have to, with the 63%, you have to draw a perpendicular line, and you have to find, and that's take as a reference. Okay, and you have to find the torque constant with respect to the perpendicular line drawn from 63% to starting of the process variable. Okay, starting of the process, that is called as the tau constant, time constant, that is the dead time. T is dead time, and parallelly we know that process gain is equal to change in and change in process variable divided by change in controller output. Okay, that is called as a process gain. Okay, so once if you know that GP, TD and tau, then you can able to find out the you can able to propose the controllers. Okay, so for that what happens, I'm taken already different systems for the same transfer function system. Okay, for same transfer function system. Okay, I'm giving so we don't go for PID any controllers. Right, this is open loop system. Okay, the system is framed as a for open loop system. Okay, this is a step signal and this is a response what you're getting from the system. Okay, so this is a step signal, this is signal, this is a defined input, and this is a what is the actual output you're getting out from the system. Okay, this is a desired output, this is the actual output what you're getting from the system. So what happens here, the difference between the delay, that means this is actual output. Okay, so this is output, this is output we're getting from that system. Okay, what happens, the difference between the actual what's a start, that means you can able to find here this is a process system is starting here, but actually the system is starting here. Okay, so what's the difference between this actual system and the process system? Okay, that is called as a delay time, or you can say that it's called as a dead time. Okay, after that once the process started, from the process started, okay, we know what's the year, this 100% of the process variable. Okay, response what from within 100%, what is 63%, down perpendicular down 63% line, and from that we are down perpendicular line. Okay, that will meet in the x-axis. Okay, so we have to find out what's the difference between the process variable starting time, okay, in the output of this in the process parameter with respect to 63% of the value. Okay, that is called as a tau constant. And if you coming here change in control variables, so you can able to find what's difference between this defined output and the first initial output. That is called a change in controller gain, and this is change in process variable. What is the initial response, what is the final response? Okay, for this entire process parameter, that is called as change in process variable. Okay, so GC is equal to change in process variable divided by change in control variable with respect to percentage. That is called as GC, and you know the tau constant, and you know the dead time. Okay, once if you know this all the three values, you can able to calculate the control, you can able to find out the system's response. Okay, that is called as Cohen tuning method. So if you go into controller type, we are having same proportional controller, proportional intercontroller, proportional derivative controller, and proportional interval derivative controller. So what happens, you know the time, tau constant, time constant, dead time. Okay, and GP. Okay, so I'm going to work for proportional first time. The system will be done by this for the open loop system, and once you find that all the things, then try to go for controllers and find out what's the response is coming. Okay, so I'm going for this open loop system, and this is the function systems. Okay, so what happens, go try to run the system. Okay, and try to find out what the scope is coming here. So this is the system scope is getting here. This is step input and this is the process output. Okay, so what happens, so this is the response what you're getting for the open loop systems. Okay, here what happens, this process variable is started. Okay, the process variable is started, this is the input response. So we have to find out what's the dead time. Here what happens, this is the thing, the process variable is started after this actual input. But if you coming here in this, what happens, this actual input, the process time is somewhat delayed here. But here what happens, if you come into this scope here, okay, this actual input is there, the process time is started after the actual time, but there's some delay. Okay, how we can able to find the delay means go here. Okay, and you can zoom with respect to x-axis. Again I'm going for zoom with respect to x-axis. Yeah, you can able to find from 1 to see somewhat is delay. Actually what happens in this point, this customer is actually meeting here, and after that is meeting up to something 1.01 and 1.02. what happens, somewhat difference is there, slowly it's having difference and having a vast difference from this point. You have to find out what's the vast difference here. Okay, so again I'm going for 1.01 to 1, this difference. Yeah, so you can able to find out the difference is 1.06, we can say that 1.01 roughly. Okay, so 1.01 roughly. Okay, so what happens over here. Okay, so we have to go to calculator. So 1.1, we can go for 1.1 itself. 1.1 minus 1 is equal to 1.1 minus 1 to 0.1. Okay, so what happens here? Delay time is, okay, so delay time is getting is dead time is, sorry, TD, okay. So what happens? TD is 0.1. okay, then you have to find out what's tau constant. Okay, so how we get the tau constant means you can go to here. So already what happens, we can find it from the starting point. Okay, from the starting point to 63%. Go to here. What's this is starting point? What 63% is coming here? Okay, so draw 63% coming approximately here. So from here to here, what happens? This point is coming exactly to 3.3, not 3.2, 3.3. So approximately 3.3. So what's the steering? 1 minus 3.3 minus 1. That means calculator 3.3 minus 1. So 2.3. So 2.3 is coming. Here what happens? Tau. So tau I am indicating that form of T is equal to 3. What's the answer is coming? 3.3 minus 1 means 2.3, I think so. Answer is coming 2.3. Then after that we have to find GC. Okay, GC is equal to what's the formula here? GC is equal to change in process variable by change in controller output percentage. Okay, so you can go for a graph. Change in process variable, what's happened here? Go to here. Change in process variable. So change in process variable is what? 0 to 1. It's the same. Controller variable. So this is a change in process variable is this. This is a process variable. Okay, this is the actual. This is a defined input. What's the defined input? What's the difference? 0 to 1, 1. Okay, so change in process variable. Also, this is a change in process variable. This is a change in controller output. Okay, so you can able to find the graph here. Change in process variable, change in controller output. Okay, what happens here? Coming here, this is a change in process variable. This is change in controller output. Okay, change in controller output is also 1. Change in process variable also 1. So 1 divided by 1 percentage is equal to 1. Okay. If any difference is there, you can able to find the difference. But since it indicates 1, change in process variable is also 1. Change in controller is also 1. What happens here? 1 divided by 1 percentage is equal to 1. Okay, 1 percentage. 1 percentage means 100. 1 percentage means indicates 0.001. So 1 percentage means it indicates it's a percentage. So sorry, it's a percentage only. Okay, so this is equal to 1 percentage only. So what happens here? So 1 percentage. Okay, so what happens? 1 percentage only. 1 divided by 1 is equal to 1. So you know the TD, T and GC. Go to this formula. Okay, and go to this formula and apply the tau D and tau and GP. Okay, GP or GC, what I said, sorry, GP. Okay, and GP means indicates the gain, process gain. If you know that we find the values, tau is equal to 2.3. So I indicate T is equal to 2.3, tau is equal to 2.3, and tau D is equal to time is equal to 0.1, and GP. Okay, sorry, GP process gain is equal to 1. Okay, if you know all the three values, try to apply these three values in this formula. Okay. Try to this formula, and you can able to find out what's the value of proportional controller, what's the value of PI controller, what's the value of PD controller, what's the value of PID controller. So, okay, for example, you can find the values of proportional 1.03 divided by 1. Okay, 1.03 divided by 1 into tau by tau. What's the tau formula? What's the tau formula? Tau, what's the answer? We got it. Tau is 2.3, tau D is 0.1. So you can go for 2.3 divided by 0.1. What's answer is getting? 2.3 divided by 0.1. 23. Okay, 23 you are getting. 23. Okay, 23 plus 0.34 plus 23 plus 0.34 23.34 into already GP is 1 into 1.03 into 1.03 into 1.03 24.402. So you have to apply the proportional control is 24.042. Okay, so if you find the as like that, we have to find the PI controller, PID controller, PID controller. Okay, so for example, if you take the PID controller, the proportional value is some formula is changing. Again, you have to apply the formula. Okay, again you have to apply the formula. Okay, for example, here I am saying that for proportional controller 24.402. Okay, so what I am saying that, see here, go for try to add proportional controller. Okay, and try to add proportional controller by adding the sum. And I try to add the controllers also, PID controllers also, exercise number 7. Okay, so what happens? Yes, so try to change the system. Try to go for PID controllers and try to get careful functional systems and go for the step signal. Try to change things. Go for minus. Okay, then try to get for responsive systems, and I'm changing the proportional controller. Okay, so I'm changing the proportional controller, and what's the value is getting is 24.04. okay, so I'm fixing 24.04, fixing the proportional value. Okay, and I'm going for run the simulation. Getting the scope is yes. So since it's a proportional controller, you can able to find the system how far the error is minimized. Okay, often if you find the open system, somewhat error is coming like this, error like this. Okay, error is coming like this, like this. If you introduce a proportional controller, somewhat the error is minimized. Again, if you propose the PI controller, by already find the tau constant, dead time, and the process gain, calculate all the things, we can able to find the proportional controller, PID controller, PD controller, and finally if I apply PID controller, okay, the response is coming like this, and we can get the stability system from this point itself. Okay, so to find out the stability system or to maintain the process, that means process variable into controlled variable. This is a controlled variable, this is a process variable. So we have to put the process in control variable. You can propose the controllers, we can go for PID controllers. Anyway, the tuning controllers are having 3 methods. One is manual tuning method, you have to tune manually. Okay, with respect to proportional gain, integral gain, and derivative gain, and you have to find the stability system. It's somewhat technical method, it takes so much time. But coming to the next method, Ziegler-Nicholas method, okay, we have know the Kc value. Okay, once you find the Kc value and Pc value, the Kc is the critical value and Pc is the ultimate period time, you can able to find out the proportional corresponding gains, and if you propose these gains, you can able to find system stability or not. We can able to check this thing. Okay, and if going to next method, Cohen Coon tuning method, first you have to go and make an attempt the open loop system. Okay, for the open loop system, this is the what is output getting from the system, and this is the actual output. You have to make comparison of these two things with the actual process, proposed output, actual output with the what's the process output. And you have to find the dead time, tau constant, and the gain. That means process gain with respect to the formula, changing process variable by changing control variable. Once you find all the 3 variables, apply these things. If you want to go for PI controller, apply the same value and try to find what's the proportional gain and what's the interval gain. And to come into the proportional derivative controller, find out what's the corresponding proportional gain and what's the derivative gain. If you had an idea to propose PID controllers, go for proportional gain, interval gain, and derivative gain. Okay, so this is the method we have to adopt this in the MATLAB. Okay, I am showing the 2 exercises. Exercise number 6. This indicates the first you have to go for open loop system. Okay, and try to find out what's the proportional gain and try to change the open loop system to closed system by proposing the sum and PID controllers. What are going to propose? Okay, and try to apply the corresponding value and find out what's the response is coming. If you come into this side for the experiment number 6, okay, this method is a Cohen cooling method. This method is what method we have said previously, second method, Ziegler-Nicholas method. Okay, Ziegler-Nicholas method. Okay, once if we find that critical value and the PC ultimate period, okay, without by the closed loop system itself, okay, we can able to find out, we can able to fit the system stability. Okay, that is by proposing 3 controllers. Okay, so this is the things what I have learned from the tuning controllers from the 2 methods. One is Zeigerman tuning method and one is the Cohen cooling method. Okay.